You know, there are these invisible battles raging all around us, all the time. I'm talking about in your morning coffee, deep inside your car's engine, even in the tiny cells that make you you. These are the great battles of the fluids, and they're all decided by one single powerful property: viscosity. Okay, so let's just start with a super simple question. Why is it that water flows so freely, right? It's just easy going. But honey, oh, honey takes its sweet time, doesn't it? It clings to the spoon, it's stubborn. It's almost like they have different personalities. And today, we are going to unpack the physics behind that personality. So on one side, you've got your stubborn, thick honey, and on the other, you've got easygoing, thin water. Now, in physics, we have a proper name for this temper or this thickness. We call it viscosity, and really, it's just a fluid's internal friction, its own resistance to flowing. Honey has a really high viscosity, and water, well, its viscosity is super low. But what's really cool is how this whole thing works on a microscopic level. I want you to imagine the fluid is like a deck of cards, right? If you push that top card, a little bit of that force gets transferred to the card right below it, and that one pulls on the one below that, and so on and so on. This sliding motion between the layers, that's what we call shear. Now, that force you're applying to get those layers moving, that internal friction, it's got a name: shear stress. Honestly, the easiest way to think about it is just, it's the push. That's it. It's the push you're giving the fluid. We use the Greek letter tau for it. Okay, so you give it a push, what happens next? Well, how fast do those layers actually slide past each other? That's the shear rate. It's all about how quickly the speed changes as you go from one layer to the next. Now, don't let the math here scare you. That delta U over delta Y just means the tiny change in speed over a tiny change in distance. So think of it this way. Shear stress is the cause, the push, and shear rate is the effect, the speed you get out of it. And this, right here, is where the genius of Isaac Newton just shines. He figured out that for a ton of different fluids, there's this beautifully simple connection between the push and the speed. The more you push, the faster it goes. It's a straight line, a direct linear relationship. The shear stress is just some constant multiplied by the shear rate. And that constant, that magic number represented by the Greek letter mu, well, that's it. That's the dynamic viscosity, the true personality ID of the fluid. And what's just mind-boggling is how many fluids actually follow this simple rule. We're talking water, air, alcohol, oil, basically most of the everyday fluids you can think of. We call them Newtonian fluids, and they are, without a doubt, the bedrock of how we understand the way fluids move. But hold on, a fluid's behavior isn't just about its viscosity. Nope, there is a constant battle going on inside every single flow, a tug-of-war between two opposing forces. In one corner, you've got inertia. That's the tendency of stuff that's moving to keep moving. It's the mover. And in the other corner, you have viscosity, that internal friction trying to slow everything down, to calm the flow. So in this epic battle, how do we keep score? How do we know which force is winning? Well, we use a single incredibly powerful number. It's called the Reynolds number, or just RE for short. The Reynolds number is, at its heart, just a simple ratio. That's all it is. It's the strength of the inertial forces divided by the strength of the viscous forces. So if you get a high Reynolds number, that means inertia is winning the battle. If you get a low Reynolds number, viscosity is in complete control. And this one number, believe it or not, splits the entire universe of fluid dynamics into two completely different worlds. You have the low Reynolds number world, where viscosity is king, and things get really, really weird. This is the world of bacteria, trying to swim in what, to them, feels like asphalt. Then you have the high Reynolds number world, where inertia is the king. That's our world, the world of airplanes and rivers and baseballs. Seriously, let's take a quick trip to this low Reynolds number world. It is a place where your everyday intuition just completely breaks down. Inertia is so weak that if you stop pushing something, it stops instantly. There is no such thing as coasting. Can you imagine trying to swim in a pool of molasses? You couldn't just paddle back and forth. You'd go absolutely nowhere. It's why bacteria have to use this clever corkscrew motion. And it gets even weirder. A simple flow in a corner can create an infinite series of tiny, nested whirlpools. It's a truly alien environment, all because viscosity runs the show. Okay, so what about our world, the high Reynolds number world, where inertia is in charge? You might think viscosity doesn't even matter here, but oh, it makes a very clever last stand. Right at the surface of any object, Doesn't matter how fast the flow is, viscosity creates this super thin region called the boundary layer. And the reason this layer exists is because of a fundamental non-negotiable rule called the no-slip condition. It just means that fluid molecules that are physically touching a solid surface stick to it. Their speed is zero, period. So inside that thin boundary layer, the fluid speed has to go from zero, right at the surface, all the way up to the full speed of the flow. And that creates this intense zone of shearing where viscosity suddenly becomes critically important again. And here's the kicker. That tiny, thin layer, it's responsible for almost all of the friction drag on an airplane. Wow. So what happens when the battle between inertia and viscosity is a close call? When the Reynolds number is kind of in that murky middle ground? Well, that's when things get really, really interesting. Smooth, orderly flow can just suddenly break down. This is the absolutely fascinating world of hydrodynamic instability. You start out with a smooth, predictable flow. We call it laminar. But as you crank up the Reynolds number, you hit a tipping point. The flow becomes unstable, and it can just spontaneously erupt into these beautiful, organized patterns, like these mesmerizing donut-shaped vortices you see here. But if you push it just a little bit further, all that beautiful order collapses into the swirling, unpredictable chaos we call turbulence. But even here, right on the edge of chaos, there's this hidden simplicity. There's a profound insight called Squire's theorem, and it basically tells us that to figure out when a flow is going to go haywire, we usually only need to worry about the simplest two-dimensional wobbles. They are the most dangerous ones, the troublemakers that grow the fastest and kick off the whole transition to turbulence. Now, these ideas of stability and chaos, they are not just some abstract theory. They have huge impacts across every scale you can possibly imagine. We're talking from the nanometer-sized air gap in a hard drive to microorganisms teaming up to swim, to the oil that keeps our car engines from grinding themselves to pieces, all the way up to the planetary jet streams that are driven by temperature differences. It's all governed by this very same battle. And you've got to check out this stunning example from biology. In that high viscosity, low Reynolds number world of reproduction, some sperm cells have actually figured out a clever trick. They form teams. By swimming side by side, they can literally reduce their total drag. This is pure hydrodynamics at work, and it allows them to swim about a third faster than they could on their own. It's incredible. Now, in our world of engineering, viscosity has massive consequences. It causes energy loss, what we call dissipation, and when you're pumping fluids through pipes, this loss is incredibly sensitive to the pipe size. It's actually inversely proportional to the radius to the fourth power. So what does that mean? It means if you make a pipe just a little bit smaller, the energy you need to pump the same amount of fluid just skyrockets. If you put the radius in half, you need a staggering 16 times more energy. That's the power of viscosity in action. So we've spent all this time talking about these well-behaved, rule-following Newtonian fluids. But what about the rebels? What about the fluids that just don't follow Newton's simple linear rule? Well, welcome to the weird and wonderful world of non-Newtonian fluids. Think about ketchup. You know how it is. It's this stubborn, thick blob in the bottle, but as soon as you shake it or smack the bottom, as soon as you apply shear stress, it thins out and flows easily. We call that shear thinning. And then you have the complete opposite, shear thickening. A mix of cornstarch and water is the classic example. You can slowly run your fingers through it, no problem. But if you punch it, it instantly becomes as hard as a rock. These rule breakers are just a fantastic reminder of how important that simple Newtonian baseline is for making sense of the entire fluid universe. So when you boil it all down, the main thing to remember is this. A single, simple, linear law helps us understand how fluids behave on scales from microscopic bacteria all the way up to entire planets. It dictates the line between orderly flow and utter chaos. And that just leads me to one final question for you to think about. What other beautifully simple rules are out there, just waiting for us to find them, hiding in all the complexity that's all around us? Thanks for joining me.